Okay, let's go ahead and get started. So today we're going to start with what we had studied before. We're going to kind of backtrack a little and go over the problem a little bit more in depth, or just review it, I'd say. And then we're going to get more into the specifics of solving this problem of the scattering of a line source from, this is a conducting strip. So in the book, what they have is a conducting strip, but the strip has some finite thickness T, which is kind of, I guess it's more of a realistic model than having an infinitely thin strip. But this kind of complicates the problem, because then you have to consider currents that are both on the top and the bottom. Technically, if it has a thickness, there are currents on both sides. Here, what we normally do for things like this, for the PECs, we assume it's infinitely thin, right? And that's more of a common approach. Why can we get away with the infinitely thin? Why is it the exact same solution? Maybe not exact same for large thicknesses, but no field inside, right? Nothing can get inside of a PEC. Very good. All right, so let's go ahead and continue with this problem. So consider an infinite electric line source placed above a two-dimensional conducting strip, has finite width W. There are various coordinate systems here that we have to be cognizant of. The first coordinate system is an X, Y, and a Z that's centered about the feed. There's an infinite line source which is placed at the coordinate origin, directed along the Z-axis of the feed coordinate system. You can see in this feed coordinate system we have the angle phi measured from the X-axis of the feed. We have an observation point. So this is our global coordinate system here, centered at the feed. All right. This is where the pattern is going to be calculated in terms of. And if you look here, we have an observation point P. There's a vector rho, which connects our coordinate origin of the global coordinate system, and also where our feed is placed to the point P of observation, right? And we have angle phi. We have the distance rho, and then the Z direction. This entire problem is invariant in and out of the board, meaning that there can be no variation. The derivative of the fields in the direction in and out of the board are 0, right? So Kz is also equal to 0. Okay, good. So then we then have another coordinate system here called the primed coordinate system. The primed coordinate system has its origin on the top surface of the scatterer, and there are points P identified on the surface of the scatterer, of which we have identified source points, right? So this line source here is going to radiate a perfect cylindrical wave, right? It has perfect azimuthal symmetry. It's infinitely thin. It's a filament, and it radiates a cylindrical wave expanding out, as if you dropped a rock in a pond at this point from out of the screen. That cylindrical wave is going to expand and impinge upon this scattering obstacle, and it's going to induce currents on the obstacle because of the conductivity of the obstacle. Those currents then will radiate, right? Once we have induced currents, then it's easy to calculate what the radiated field is due to those induced currents by using the vector potential approach, right? All right. Now, these source points are going to be pointed to by this primed coordinate system. Okay, so it's kind of confusing because this is a primed coordinate system, but in the global coordinate system, we have the primed vectors. So rho prime goes to the source point, and then we have the vector that matters for radiation, which is the rho minus rho prime, right? This vector R, capital R. All right, good. And then there are other various variables. All right, good. So we know the line source from last semester, in the absence of the strip, radiates the field, which is normally called the incident electric field, but here we're going to call it the direct field, and it is giving nothing but negative eta k Iz over 4 into H naught 2 beta rho, right? Why do we expect this to be H naught?
Solution scattering. You have the line source angle function second order.
That's right. What if this wasn't H naught? What would we know about the solution? What if it was H1? Remember what is this normally? HM, right? And then there's, what's that? Say again? Symmetric and what? Very good. So remember, these are linked. The order of the radial wave functions are linked to the order of the azimuthal functions, right? So if n is not equal to 0, then we expect there to be variation in azimuth, right? And because this line source is an infinitely thin filament and there's no possibility of azimuthal variation. So we know that the only function that could be used to describe the radiation from that line source is perfect cylindrical wave. It should be H naught, right? H naught 2 beta rho. Very good. So the line source is going to intercept, the radiation from the line source intercepts the conducting strip, induces current on it, and that conduction current density can be expressed in this form. Jz times delta x, right? If you multiply a density by a distance, then in this case, there's still per unit length in and out of the board, but you're going to get some kind of current, right? We call that delta Iz, all right? Delta Iz. So this current density radiates a scattered field denoted by Ez scattered. So this in line source is going to radiate against the conductor. It's going to induce current on the conductor. If you find the radiation due to that induced current, it is called the scattered field, all right? So the scattered field, we can calculate, we denote it as Ez scattered. So if we subdivide the strip into n segments, each having the same width, delta xn prime, the scatter field we can write in the following way. We multiply the Green's function for the current density by the current density itself, and we get the radiation due to that element. So we get the radiation due to one of these rectangles of current, and we add them up, right? Now in the limit, as these widths become very, very small, then what we get is an integral, right? So here we're summing up the radiation due to each of these segments of current multiplied by delta x multiplied by the Green's function, right? So this is kind of like a very crude, discrete version of the convolution. This is the convolution, right? The current density against the Green's function. This gives you the actual scattered field. And what matters is the distance between the source and observation, right? Because each of these segments here, if they were very small, right? Each of these segments here are going to radiate their own cylindrical wave, right? So what matters is the 1 over square root of rho decay and the e to the minus j beta rho or whatever have you, phase delay from there to there, yeah? Okay, good. Very nice. All right, so the scatter field is repeated here. The total field at any observation point, including the strip itself, will be the sum of the direct and the scatter field. Incident plus scatter is total, right? However, to determine the scattered field, we need to know what the induced current density is, obviously, right? All right. So the objective here will be then to develop the integral equation to find the current density Jz. I realize this is a review of what we did last time, but we're going to go, we need to see it once or twice, right? This can be accomplished by choosing the observation point on the strip itself. All right. So we need to develop an equation that we can use to solve for this current density, right? But what we have so far is just the scattered field. We want to find the scattered field, but we need to know the current density, right? So we don't know the scattered field, which is on the left-hand side. We do know what these constants are. We do know what our Green's function is, and we don't know what our current density is, right? So we're stuck. We have two unknowns on both sides. We don't know the scattered field. We don't know the current density. How can we fix this so we can reduce the number of unknowns and find the current density, the quantity of interest? Well, we need to know what the left-hand side is, right? What's some place that we know what the left-hand side is? On the surface of PEC. Because on the surface of PEC, we know the total tangential electric field has to be 0. So if we add to this equation the incident field, then the incident field plus the scattered field on the surface of the PEC, we know what that value is because of the boundary condition. It's equal to 0. So now the left-hand side is known. And everything is known in this equation except for the current density under the integrand, which we can find, right? So that's the idea. We need to specialize this equation, which is for points of observation anywhere, to observations to places in space where we know what those fields have to be. And those places are where we know the boundary condition. For this problem, it's a perfect electric conductor. We know what the total field has to be on the perfect electric conductor, right? So we choose to specialize this equation to observations at points on the conductor itself, all right? So at these points, we know what the sum of the direct and scatter field is due to the boundary condition on the perfect electric conductor. That is, that the total electric field evaluated on the PEC, which is composed of the direct plus the scattered, evaluated on the PEC. We're calling those observation points rho m, has to be equal to 0. All right, so the direct field, we can write this same expression as the direct field has to equal to negative the scattered field. So your book calls it the direct field. I don't like that. I like incident because it's much more commonly used. So hopefully I won't say incident on accident, right? So incident equals negative scattered if they have to sum to 0. But this is only true when you evaluate the observation on the PEC. Yeah, good. So following this boundary condition, we can replace what the direct field is. This is the radiation due to a line source in the absence of the scatterer. And the right-hand side is the scattered field from this expression here. This is an integral equation. Now we can solve it because the only unknown is this current density in the integrand. The left-hand side is known. It's the radiation due to the line source. We know the Green's function. Presumably, there are two very difficult parts of applying method of moments to solving different problems in scattering. Those two difficulties are, one, obtain the Green's function. All right. If it's a full free space problem, then we already have them, right? But there are other problems where, remember, the Green's function depends on the environment. If I have a point source or an infinitesimal dipole sitting on top of a dielectric half space, then that's a different Green's function. I have to solve for the radiation due to that dipole in the presence of the dielectric half space, right? If I have a conducting obstacle over here, a metal sphere, and I have a delta function here, a current density, a dipole, infinitesimal dipole, if I want to use this current density, this dipole, in a convolution like this with some unknown current density, then I have to find the radiation due to this dipole in the presence of the sphere. As a function of position, this dipole could be anywhere, right? Okay. The other problem that's very difficult about method of moments is what's called the self terms, and we'll get to that today. Those two problems, if you solve both of those, then method of moments is very powerful. Of course, when the problem scales to something very large, electrically large, then you have the other problem. These matrices are very dense. And we'll come back to that, or we'll get to that. This is your EFIE, electric field integral equation. All right, for a unit current amplitude, if IZ is equal to 1 amp, then you can cancel these coefficients on both sides, and you get this expression. All right, so now you should understand where this comes from. It's at a boundary condition. We use a boundary condition where we know the total field on one side of the equation so that we can solve for the unknown in the integrand. All right? Good. So, okay, so how do we solve it now? If we go back to this integral equation, what do we have? The unknown is under the integrand. Everything else is known. So we cannot do this integration here, right? We can't do this integration, first off, because we don't even know this function. So we have to do something about that. So what do? We expand that unknown function in terms of known functions with unknown coefficients. And if we can solve these integrals, then we can synthesize this current. If we can solve for these coefficients, then we just multiply these coefficients by each of these basis functions, sum them up, and we can synthesize the current, right? And that's the idea. All right. So if we take this expansion in terms of the unknown, or in terms of known basis functions that are weighted by unknown coefficients for the current density and plug it into the EFIE, then by linearity, we can factor out the summation sign with the unknown complex coefficients, and we have an integral we can solve now, right? Presumably we do know Gn of x. We choose those, right? Good. So this can more compactly be written as h is equal to the sum of from n equal to 1 to n, alpha n times f of Gn. F is called a linear integral operator, right? So you feed it some functions, right? You feed this some g of n, and it's an operator that once you feed it the input g of n, it gives you the output of g of n convolved with h, right? All right, and g is the response function, h is the known excitation, right? Okay, good. All right, the integral equation derived by enforcing the boundary condition on the PEC strip of E tangential equals to 0 at the observation points rho equal to rho sub m is the following. Okay, so I've repeated it here, right? The problem here now is that we have one equation, this equality, one equation, right? But we have n unknowns because now we've introduced these n unknowns to represent our current density. But we only have one equation. But this equation is a function of observation rho m, right? So to generate n equations so that I can solve for my n unknowns, I can evaluate this equation at n different observation points. Yeah? So to generate n equations, we can enforce the boundary condition at n different points, and we end up with this expression here. The left-hand side is the incident field. We evaluate this on the surface of the scatterer at n different points. Then we have this expression where we evaluate it at now n different evaluation points, and we integrate across the entire domain of the scatterer for now. All right? Because we don't know what the domain of Gn of x is yet. Still general. Now we have n unknowns and n equations, and we can construct a square matrix equation, a linear system to solve for these unknown coefficients. All right? We do that in the following way. So we can rewrite this expression here as Vm equals to the sum from n equal to 1 to n of Inzmn. All right? So Vm is a matrix where we sample or evaluate the left-hand side, the incident field at m different observation points, and Zmn is the impedance matrix multiplied by I. I is equal to Z inverse V. All right? Since the boundary condition was enforced at n discrete points, the approach is called point matching. We're only evaluating, or we're matching the left and right-hand side at different discrete points. Point matching, collocation, all right? All right, so we still haven't chosen the basis functions yet. The basis functions, we can choose from many different sets. So the basis functions, we have different kinds of basis functions. There are two main types: subdomain, where they're non-zero only over part of the domain of g of x, right? G of x is a function that encompasses the entirety of the scatter, right? Minus w over 2 to w over 2 in this case. But if we use basis functions, which are subdomain, meaning they're non-zero only over part of that domain, then we call those subdomain. If they are non-zero over the entire domain of the basis, or sorry, the entire domain of the unknown function g, then they're entire domain functions. All right. The subdomain functions are a lot more popular. Yes.
So if we have three basis functions, do we need like three matching points? So the matching point will be the same as the amount of basis functions?
Yeah, because if you introduce n basis functions, then there are n unknowns, the coefficients of those n basis functions. So you need n equations, right?
Okay.
If you have entire domain basis functions, then over the domain minus w over 2 to w over 2, you might use sinusoidal or trigonometric basis functions. So you have like a Fourier series over that domain. We have a constant, half a sinusoid, a full sinusoid, 3/2 of a sinusoid, and so forth, right? But each of those have their own amplitude that scales them. So in that case, you still need as many equations as you have basis functions. You need to make the system square, right? All right. So one of these is called, or the most popular, I don't want to say the most popular, but very popular set is piecewise constant, otherwise known as pulses. These pulses are non-zero only over part of the domain of g of x prime. And for example, here we're showing g2 of x prime. So this says g2 of x prime. This thing says g2 of x prime, right? And it's only non-zero over this domain. Otherwise, it's equal to 0 everywhere else. All right? And it has a unit amplitude over that domain. All right? Very good. So when you solve the matrix equation, you're going to get all of these coefficients, right? You're going to get all of these coefficients, and that means those are the amplitudes of the different pulses. So what you get here is a piecewise constant approximation to the current. So maybe the current's doing something like this, right? But if you use pulse basis functions, your current's going to look like this. All right? So that's one danger of using, but as long as the pulses are very small, then it works pretty well, right? I use these a lot. So A1, A2, A3 are different. They scale these piecewise constants, and you construct a representation of the current using this sort of a piecewise constant pulse basis function expansion set. They look like this. G of x prime is equal to 1 whenever x prime is in the domain of xn minus 1 to xn. For example, xn minus 1 is, so this is G2. So xn minus 1 is x1 prime, and this is x2 prime, right? Otherwise, it's 0 everywhere else. Okay, remember, these functions have to span the full domain, but they can be defined to be 0 there. All right. Another set of functions are called piecewise linear or triangular basis functions. These triangle basis functions are defined over 2 segments now. That's the main drawback of these. The integrations become more complicated. And they span 2 whole segments, and there are segments where they overlap each other. All right. And in these ones, you get a linear approximation to the current. So what we had before was, we said it was something like this, right? Maybe. But here, look how much better these ones do, right? Could be like that, like that. So linears are good basis functions. They're much harder to program. The pulses are very easy to program. And if you use very small pulses, you'll probably be okay. These are the 2-dimensional equivalent of what are called the Rao-Wilton-Glisson basis functions, which are basis functions which have linear basis function triangular domains. That allows you to model 3-dimensional arbitrarily shaped structures. All right. So anyway, they're defined like this, okay? And then there are also, in some cases, you might need sinusoidal basis functions. Okay, so these aren't any better than triangle, right? These are probably harder to program, but there are some instances, as your book says, where if you have a weighted integration, if you have an integral of a sine function multiplied by another function, sometimes there are closed form expressions, or it's easier to integrate those whenever you have that kind of weighting function in the integral. These are not very popular use. I've never seen a case where these are used. But these are very popular. Pulse and triangle are very popular. All right. Okay, so here's our integral equation. If each of the expansion functions Gn of x are now chosen to be subdomain type, then instead of integrating from minus w over 2 to w over 2, which we're still doing, right? Gn of x now is only non-zero over a part of the domain. So you can reduce the integrand or the limits of integration to xn to xn plus 1, because outside of those limits, it's 0, right? So it's the same integral, except if we've reduced the domain of integration because of the subdomain function being 0 outside of that domain. All right. In addition, if the Gn of x prime are pulse basis functions, then Gn of x is equal to 1 over this domain. So now you've reduced it to this. This is the easiest, right? That's why pulse are popular. However, this integration here for this impedance matrix cannot be done in closed form. All right. So you have to resort to numerical integrations. We'll go over numerical integration techniques later in the course. But for now, you can just use MATLAB's built-in function, which is called integral, which can perform adaptive Gaussian quadrature numerical integration. Gaussian quadrature is basically the king, right? So it would be really wise of you guys to look into this Gaussian quadrature numerical integration. I'll probably try to teach it to you later this semester, but it's a really interesting approach. All right. Otherwise, we can do a crude. So you guys are learning this stuff for the first time ever. So the first thing you always do is do this crude but effective approximation called the midpoint rule. If these segments are small enough, then the integrand is assumed to be constant across this domain. And if it's constant, then you can factor the integrand out of the integral. So then you can just multiply the integrand by the domain of integration, right? Delta. But you have to evaluate the integrand at the middle of your integration domain. Hence the name midpoint rule. All right, so in that case, Zmn would be equal to negative delta, where delta is the integral from xn to xn plus 1 of dx only, which is the width of the pulse, times this integrand evaluated at the center of the domain. All right. Yes, that's correct. That's good. Okay, yeah. So this needs to be, but those points are assumed to be in the middle of the segments anyway. All right. Okay, so what could be the problem, right? So we have now this integral. We have to solve this. We have to solve it n squared times, right? Because n by n is a square matrix. Mn is a square matrix of n by n. So you start off with 1m, the first row. Remember, the first index is row, then column. So Z1n is the first row, and that means m is equal to 1, which means you're looking at the first observation point here. And as n increases, the source points are changing. The current density is the n, right? X prime. So this pulse basis function, all the current from it radiates to here. That's Z 1, 2. If this is X1, X2, so forth, right? So then you consider this pulse here, worth of current. That one, when it radiates, you compute the matrix element to that point of observation. And this is called Z13. And these go in a matrix where we have Z11, 12, 13, ... right? Here we have ZNN, ZN1, and so forth, right? Okay, so why do we have to calculate the field due to all of these pulses and add them up here? What do you think your feeling is for that?
The contribution of each part, that initial point.
Very good. Why do we need all that though? Yeah,
Because we're trying to approximate the surface current in the first place, or the current distribution in the first place. So unless we consider all of it, it's not a good approximation.
that's kind of part of it, but not what I'm looking for. Any other ideas?
Oh, we need the E scatter.
What's
but
that?
We need the E scatter. So
Okay,
yeah, we need that just gives us the local. But yeah, we needed all the contribution, all the neighbors sections.
so what's happening at this exact point here, right? What's happening here? What does this equation even mean at that point?
Tangential electric field at that point is U.
The tangential electric field at this point has to be what?
It's U.
Because that's what this equation is enforcing. So what is the tangential electric field at that point? The incident field plus
This kind
scatter field due to the rest of the structure. All this current radiates. You have to add up the electric field due to all of this current at that point to get the true total electric field there. That has to be equal to 0. So each row of the matrix equation, or this equation evaluated for all different n, but at each m, at m equal to 1, is saying the boundary condition at that point has to be satisfied, which means the radiation due to all this current added up at that point, giving you the true total field, has to be set equal to 0, right? Okay. Then you move to this point and you do the same thing. Find the radiation to here, there, and so forth, right? All right, so the total electric field at this point is not only due to the neighboring currents, but also due to this current here in green, right? We need to find the total electric field at this point, which includes the electric field radiated by the current in the cell of observation. That is called a self term when the source current is in the same cell as the observation point. All right? What's the problem with the self terms? Why are they different? Because the integrand, this integrand here, becomes singular as rho m approaches to rho n. So they provide difficulty, right? So the integral equation is constructed by enforcing the boundary condition of vanishing tangential total E. The total E is consistent of the summation of the direct or incident field and the scatter field. The scatter field originates from all segments carrying surface currents on the scatterer, including the segment where the observation is being made. So here, ZNN now, if it's a self term, then M is equal to N, right? So ZNN, which is the diagonal of that impedance matrix, is equal to, this is the expression for ZMN, but now I should have probably made that an N. This should probably be an N as well. Same here and here. And what is the Hankel function of order 2? That's equal to J naught minus J Y0, right? We know Y0 is equal to infinity when its argument goes to 0. So this becomes sort of 1 minus infinity, right? J infinity. So it's singular. All right. So what can we do to what can we do to move forward with this problem?
It is possible to use the integration path in the complex plane around that point.
Let me think about that. That's a good thought. So you're thinking about avoiding the singularity by doing this. Integration's in a real domain, first off. It's dx prime, but maybe you could complexify it and extend it, analytically extend to the complex and integrate. Maybe that's cool. I like that line of reasoning or thinking. But we could do something a lot easier. So first off, I want to go back to something that Mikhail said last lecture. Was he was talking about the uncertainty in the Hankel function as it blows up, as it becomes singular. And I didn't really understand what he was saying, but now I think I understand what he's saying. If it becomes singular, if this argument goes to 0, this Hankel function, you think you can just evaluate it on the computer by typing Bezel H in MATLAB. But as it becomes more and more singular, the numerical routines which calculate these Bessel functions become less and less accurate, right? It becomes more difficult to synthesize a singularity. So I think that's what he was referring to, that that these things become uncertain. The evaluation of these numerical functions have some uncertainty built into them as the function becomes singular. I believe that's what he meant. But anyway, what we can do is something which is commonly done. We can take this Hankel function, and it has a small argument expansion. There is an approximation to this function when the argument goes to 0, and that is this expression here. 1 minus j 2 over pi into 1.781 beta rho minus rho m over 2, right? You guys have seen this last semester for sure. We went over this. Now you see where this Euler number comes from, this constant 1.781. In that program I showed you in the first lecture, I said there's a constant 1.781, Euler's constant, and you'll find out what that is later. It comes from these subterms, the small argument expansion of the Hankel function. All right, so you're going to evaluate this integral because everybody needs to do that once in their life for self-terms of method of moments in your homework. All right, so expect that coming. You got to do this integral. I'll give you some hints right now. This thing is singular. So first off, the first hint is you don't need to go xn to xn plus 1, right? Because the self-terms are all the same. You just need to go from 0 to delta. So when you do this in your homework, change the lower limit to 0, the upper limit to delta. Then what you're going to have is an integral from 0 to delta here. And you're going to have to take this absolute value here and split it into 2 integrals. All right. Look up how you integrate absolute value functions. You split it into 2 integrals. That'll be enough hints. I think you'll get it from there. All right. So here's the result, though. I've done this once or twice. And this is the result, right? So now for your self-terms, you can integrate the singular function. It's an integrable singularity. And now the diagonal terms you can evaluate, they're all the same. They're this. If you have a uniform discretization, right? All right, so since this result is valid for all terms when m equals to n, if it's a uniform discretization, it appears across the diagonal of all the impedance matrix. But you can use the same function if it's non-uniform discretization, just these deltas will be different. So it won't be the same number across the entire diagonal, but the same function will apply for different deltas. Yeah.
I've seen some integral equations formulations where they just remove the diagonal elements, or they'll like treat it when they formulate the integral equation. Like, have you seen-
That is probably not, you probably might be misinterpreting that because as far as I know, it's impossible to ignore the diagonal. They're the ones that give you the most contribution.
Okay.
Everything starts to die off from the diagonal outward. So if you get the diagonal terms wrong and you do everything else perfect, your current density, your solution will be way off. Those ones affect the solution the most. But you can show me that paper sometime. I'll look at it and see. Maybe I'm mistaken. I've never seen that before. Okay, good. So let's take a look at what happens when we just do point matching. All right. So the point matching collocation approach applies to the boundary condition at n, applies the boundary condition to n discrete points, right? At unique points to generate the n equations needed to solve for the n unknowns. However, this approach only guarantees a vanishing tangential electric field at those n discrete points. At points in between those n discrete points, the boundary condition is not required to be satisfied. So it's not guaranteed to be zero, the tangential electric field. For example, these figures taken from our emeritus professor of this university, Stutzman, right? He wrote the antenna book, my favorite one when I was coming up through school. These are from his book. So for example, the figure to the right shows the normalized tangential electric field along 1/2 of a center-fed dipole with pulse expansion functions and delta weighting functions. All right. So here's the center, here's the end, here's z over lambda. So how long is this dipole? What is L?
Stop quickly.
Yeah, I wonder if this is in, so this is z over L, right? I guess it's normalized, right? Not a particular dipole. It's some length L, but you go to the center here, right? Okay, so the dots here indicate where we did the point matching. Those point matching happen to give you zero, or they should give you zero, tangential electric field, real part, and imaginary part of the tangential electric field at the match points. But look, in between these match points, the tangential electric field is not zero. And that will lead to inaccuracies in your current solution, right? Because the correct solution for the current at the end, if you calculate now the tangential field, if you got the current exactly right, and you go back in and calculate the tangential field on all points on the dipole, the boundary condition should be zero everywhere, right? Even using vector moments, that probably won't be possible, right? Because the best we can do, because that will be an infinite number of points, right? So we can only either match at these points or do one thing better, which we're going to explain in the next slide, all right? All right. So point matching is pretty good. It's used a lot, but it's not as accurate as using weighting functions, testing functions. So we may define the residual as the error in the tangential electric field at all points on the surface of the scatter, which is the incident in the scatter field, which is going to be which is not equal to zero on the surface of the conductor, right? The error, the residual, you want it to be zero. That means tangential E is equal to zero, right? So to minimize the residual in such a way that its overall average over the entire structure approaches zero, we use the method of weighted residuals is utilized in conjunction with the inner product, all right? So we need this inner product. This inner product is sort of the functional inner product. Remember I was telling you guys about the inner product between vectors, A dotted with B, and if you wanted an orthogonal function, then the A dotted with B, or sorry, orthogonal vectors, A dotted with B had to give you zero. And if you extend that concept to infinite dimensional vectors and call them functions, then you get this inner product between functions. If this inner product is zero, then these two functions are orthogonal, right? All right. So if they're complex vectors, you need this conjugate in general. And they have these properties. These are all linearity and positive definiteness and all of that, all right? Okay, so this technique we call the method of moments, or the moment method. The moment method is an approach to solve an integral equation, all right? It does not lead to vanishing residual at all points on the surface of the conductor, but it forces the boundary conditions to be satisfied in an average sense over the entire surface. So I don't know if you remember last lecture, at the very beginning, I said, well, we can use these pulse basis functions. We can average over the unit cell, average over the domain of one of the basis functions, the electric field, to try to satisfy the boundary condition in an average sense. All right, that's what we're doing here. So to accomplish this, we define a set of n weighting, or we call them testing functions, Wm, 1 through n, in the domain of the operator f, right? Operator f was the integral operator, and we form the inner product between each of these functions. We obtain the following. This was our equation we derived from before, right? This is our EFIE. The incident field is equal to the current coefficient vector multiplied by basically the impedance matrix, right? Now we take the functional inner product with both sides of the equation against our testing functions. So now we have Wm dotted with h integrated, and we have Wm dotted with the integral operator on the right-hand side, right? Okay, what is that going to do? That's going to satisfy the boundary condition in average sense over the entire surface, because we're weighting this residual function to zero. So we can write this in matrix form like that. We'll go over an example of this, right? We have Fn Mn. So now when we fill this impedance matrix, it's not just going to be what we had before, which was ZMN, the integration of these the integrals of the Hankel function. Instead, it's going to be the integral of the Hankel function and then integrated. So this term right here, for example, is going to be, because of this operator here, it's going to be the integration. So these are 1D. So let me, this one is going to be the integration over x, integration over x prime. And we have w, well, you know what? Let me write it like this. xm to xm plus 1, wm, multiplied by the integration of xn to xn plus 1 times f, which for pulse basis functions that are subdomain type, we found as h naught to beta rho m minus rho m dx prime and then dx, right? So now this is what we had before. Now we're multiplying by a weighting function, integrating over that domain as well. So the integrations become double integrations, right? Rather than single integrations. And we're projecting this scattered field term onto these weighting functions, a space with the weighting functions, right? On the left-hand side, we're projecting them onto the same weighting functions. We're equating those projections. Because this looks like a projection, right? Okay. So when you first look at this stuff or learn it, you just have to see it and kind of, get the gist of it. Then you go to your homework and you write it out. That's where you really start to, do I understand this? You write it out, and as you're writing it, you're kind of teaching it to yourself because you're deriving the expressions, and you won't be able to write the English that explains the math that you just wrote down unless you understand what you're writing down, right? So that's when you really start to understand it. And then still you don't understand it because then you have to go program it. And that's when things become crazy. So you're going to learn this when you go to program it. All right. That's when you have to sit and think about it, which you'll do in your homework. So when Wn equals to Gn now, so when the testing functions are the exact same as the basis functions, you use the same set. Then the testing functions, that's referred to as Galerkin's method. All right. Okay, that's referred to as Galerkin's method. All right. That's very popular, right? Galerkin's method. That's what I use all the time. It's most widely used. So when the testing functions are chosen as Dirac delta functions, rather than the same as these would be pulses, right? If we use pulse, Gn is pulse, then the testing function is also pulse. All right. Okay, let's go back to this. If they're pulses, if Wm is pulse, then what happens? Then this is just one, right? So this becomes the integration xm plus 1, xn plus 1, just h naught 2. Beta, rho m, rho n, dx prime, dx. So what's the difference between this and this? The only difference is we're averaging, where is that? Here, right? The only difference is we're averaging this result. The outer integration is averaging it over the domain of the test function. Because now we're integrating over xm, the nth pulse, which is the testing pulse. So we just take this result. If I put it in brackets, it's the same as before. And that other integral is an average. It's technically a weighted average, but the weighting function is a pulse of unit amplitude. Now we're averaging this result in the observation pulse instead of evaluating it at the center like we did here. Where was that? Yeah, instead of calculating the integration from, or the radiation due to all of the current of all these pulses of current and evaluating at the center, and only applying or enforcing the boundary condition at the center of the observation pulse. Now we're calculating the electric field due to all of these current pulses and evaluating them over the whole pulse and averaging that electric field. Now we get total tangential electric field averaged over the domain of that cell, which is better than just enforcing it or evaluating it at the center of the cell, right? Okay,
So if you were to like do that numerical integration with like quadrature or something, you'd be breaking up that small interval into a bunch of segments and like computing the like Hankel function or each PM with P or row M with row N.
okay, quadrature, you mean evaluating these matrix elements from quadrature, right? Means you take this current here and you integrate over this domain as the current. The Hankel function itself has row M and row N. It links the source to the observation point.
Yeah, and numerically, you'd have like a bunch of row N's within that interval that you're like performing the Hankel function evaluations at.
No, okay, so what it does is it takes that integrand and it expresses in terms of a series of polynomials. In particular, you evaluate the integrand at points that are taken from the Legendre polynomials. And there's a property about the orthogonality of the Legendre polynomials that allows you to convert that integration into a summation of the integrand at particular points, which are defined as the zeros of the Legendre polynomials. And you weight them by certain weighting coefficients. So you convert this integration into summation. And it's exact. It's really cool. I'll teach it to you guys probably. If not, read up on it. All right.
So basically, the domain both integration are the same. Is that what you're saying?
The domain you're talking about yeah, where was that? Here? No, here. Where were we here? The domain, no, this one is xn, the nth pulse. This is the current, the source. This integration, the inner integration, is over the source segment. That source segment has current in it that radiates, right? So here's the source segment. Let's say this is xn. Here's the observation xm.
No, for the
For the what?
diagonal.
Yes, the diagonal term, these poles would be the same, right? So you would have current and you're observing. So this is a whole pulse of current, right? So it radiates onto all of itself. This part of the current radiates everywhere here, right?
Means we do the integration twice.
Yes. So your ZNN here is going to have, I can't remember if this was, yeah, you know what? This might be due to, so probably I should have, no, because if this was done twice, and there would probably be, yeah, this is point matching. Because if this is done twice, you'd have delta squared, right? So yeah, normally if you use Galerkin's method and they're both pulses, then this would be different. It's more accurate, right? All right. Good. Okay, so when the testing functions are Dirac delta functions now, then they are this set of delta functions at the center of each pulse. If I do the functional inner product at the left and right hand sides of this EFIE, then what will I get? Well, if I take anything and I integrate it against a delta function, then I just evaluate the integrand at where the delta function is non-zero. So I get back to point matching, right? So point matching can be seen as testing functions, which are Dirac delta functions, right? Yeah, weighting functions, which are delta functions. Okay, good. All right, so, okay, if we test the EFIE for the conducting strip, this is the EFIE here for the conducting strip. If we use the inner product specialized to the conducting strip geometry here, this will now be not integration over S, but it's going to be integration of minus W over 2 to W over 2, W conjugate dotted with G dx, right? Then we obtain the following. So this is still very general. These are general functions, which could be subdomain or could be entire domain. Same with the W's, right? These are either subdomain or entire domain. We obtain this expression here. We call it primes because we distinguish that it hasn't been specialized to the choice of testing or basis functions yet. So the left-hand side is the incident field. So it's kind of confusing because it's not confusing, but this looks like a Green's function. This is a Green's function. This is not. This is a cylindrical wave from the source, the line source, the incident field technically. This is a Green's function, all right? So be careful with that. But incident field multiplied by the conjugate of the testing function integrated over the total domain gives you the voltage vector. And the impedance matrix is weighted integral or testing the scattered field. And the scattered field is found by the spatial convolution of the current density and the Green's function, right? All right. So now if they're both subdomain type, these limits of integration can reduce to only where the subdomain basis and testing functions are non-zero, xm to xm plus 1 for the testing function, xn prime to xn prime plus 1 to the basis function. All right. So I'm pretty excited you guys are learning this because this is super powerful and it's super useful. And it gives you so much power in electromagnetic theory and scattering and all kinds of things, right? So there are two ways to approach solving problems or doing design and in electromagnetic theory, like antennas and stuff. I don't want to say one of them is better or not than the other, but you can learn to use software in terms of like commercial tools. Somebody's already done all of this, learned it a long time ago, and built a commercial product out of it and sold it to everybody as CST, HFSS, and so forth, right? So you can use that software, not know what's under the hood, and feed it a model and get results out and analyze it as long as you have good intuition of what you expect, and you can use those tools effectively. But it's much better to learn what they're doing, and even better, in my opinion, to write your own tools. Of course, it takes way longer to validate these things, make sure you're doing it right. But you get so much more insight. So after you learn the results or the concepts of this chapter, you'll be able to solve anything, right? You can do any scattering problem. It doesn't matter what the geometry is. Okay, there's a lot more to this. You have dielectrics, 3D, all of that. But there's no limits now because before you were only able to solve a handful of problems which had canonical geometries and solutions which were amenable to analytic solutions, right? So now you can take arbitrary geometries and you can feed it with any kind of plane wave. I'm going to teach you how to design impedance sheets next using this. And then you can design any antenna, any wavefront transformation device, any kind of metasurface where you have any illumination, and from whatever geometry, you can design a metasurface to give you any scatter field. So you can do any wavefront transformation with it, right? There's a lot of challenges with that, though. I mean, you have to somehow unhomogenize it at the end and do a unit cell design and come up with actual geometry of printed circuits that can emulate these impedance sheets that will use the integral equations to design. And then there's a lot of other challenges on metasurfaces in particular have subdomain unit cells, which means they could be anisotropic, and the impedance sheet could be anisotropic in each of these unit cells. So there's a ton of degrees of freedom. If you have an antenna or a scatter or a metasurface, which is like 10 lambda by 10 lambda, and there are the unit cells are lambda by 10, then you have 100 by 100 unit cells, which is 10,000. And then each of those have an anisotropic impedance tensor in them, which has 6 minimum degrees of freedom, right? So that's 60,000 unknowns. And you want to do some kind of optimization on that, then you have to somehow do a inverse design of a metasurface that has 60,000 degrees of freedom. But you can do that. You can do that. In fact, that's a lot of what I have done for my research. Anyway, I'm excited you're learning this stuff, right? It opens up the design space for you guys a lot. All right, good. So calculation of the radiation pattern. Now we solved for the currents. We did the inverse of the matrix. We calculated the coefficients. We went back and multiplied all of our basis functions in the expansion set by those coefficients. Now we have an approximation for the current. We can calculate the radiated pattern, radiated fields or radiation pattern due to that current. So you solve the integral equation. Now you can calculate the radiation pattern. In particular, we're calculating total field, right? That line source radiates everywhere. So the actual electric field in the far field is due to the induced currents, scattering, and due to the direct wave from the line source to the far field. So the total field is the direct or incident plus the scattered. Here's the incident field. Here's the scattered field. We use the method of moments by specializing this integral equation to points on the scatter to calculate these currents. Now we know them, right? Now we return to this. We plug the current that we have back in, and we can calculate the far field. So if it's unit amplitude, again, we can factor this out, and we can write the total field like this, incident plus scattered. This R, which is rho minus rho prime, is constructed or obtained by the law of cosines. But for far field observations, remember that if this observation point goes off to infinity, then these become parallel, right? And they only differ by that length. So you can get that length by projections, like this: rho minus rho prime cosine phi minus phi prime. We keep the actual length for the phase terms because phase can go in and out as destructive and constructive interference, and it's very sensitive to getting that correct. But amplitude, if we go to infinity or infinity plus, whatever this tiny distance is, not gonna be a different amplitude. But this distance could be half a wavelength, right? And that could give you destructive interference if you try to approximate the phase terms also as just rho. All right. So since we're going to the far field, the observation point, the argument to the Hankel function now, instead of being 0 for self terms, is infinity, right? So we use the large argument expansion for the Hankel functions. Here we have it in terms of n, but for 0, n equal to 0, you get this expression here. And the total field, by substituting in these expansions, large argument expansions for these Hankel functions, we end up with this expression here. And this expression, if you factor out some common terms, right, the e to the minus j beta z. And if you normalize everything, which is common, then you get this expression, right? So you can calculate the far field now, knowing the jz you obtained using the method of moments. Yeah, cool. So let's do a quick example taken from your book. You have an electric line source feed, as in this figure to the right, and W is equal to 2 lambda. The thickness here is lambda by 100. So it's basically infinitely thin, right? And the height of the feed, h, is half a wavelength, right? This is h from here to the feed. We want to calculate the induced current density using the method of moments and compare the physical optics current density. We're instructed to subdivide the strip into n equal to 150 segments using pulse basis functions and point matching. So here's the current that you solve for, right? And you guys will get a chance to do all of this. Here's the current that you solve for. The integral equation with point matching gives you the solid curve. If you just use physical optics, so physical optics here, 2n cross hi, where n is y hat, right? This is the surface here. N is y hat. And the incident magnetic field due to what is the incident magnetic field due to the line source, right? You take your thumb, you put it in the direction of current, and your fingers by Ampere's law curl in the direction of magnetic field. So the magnetic field is completely azimuthal, phi directed, phi hat, right? So you get phi hat, and you evaluate this on the strip. So phi hat can be expressed as negative x hat sine phi plus y hat cosine phi. I don't know why I have this there still. This is a mistake. Okay, and y crossed with negative x is z, right? So this becomes 2 times z times sine of phi times h phi incident because of this sine of phi, right? Good. Now, the next thing we do is we evaluate this h phi incident, which is h1 2 beta rho m times beta over 4, I think, times iz, right? So, and evaluate this at rho n, which are the points on the strip itself. And you get this expression at the end, all right? So that's physical optics. So this is what the physical optics looks like. It's this dashed line. It agrees pretty well for the middle, but it doesn't have any information about the finiteness of this structure, right? We just evaluate the magnetic field here. So you don't see these singularities that build up in the current on the ends. PO doesn't capture any edge effects, all right?
So this is using point matching, not any testing function.
Point matching, yeah. No, yeah, okay, point matching is like delta function testing functions, but yeah, point matching. Point matching and pulse basis functions. So it does pretty good, right? And it gives us a numerically exact current, right? And it's not restricted. This approach is not restricted to particular canonical geometries. Remember we did scattering at the end of last semester? We could only solve problems that had spherical symmetry, cylindrical symmetry, or planar symmetry. We did scattering from plates that had finite width or infinite length. We did scattering from cylinders, dielectric-coated cylinders, or we did scattering from PEC spheres because we needed to use the wave functions, which were specialized for those coordinate systems, right? So we can only solve scattering of canonical geometries. Now, with this approach, you can solve scattering from any geometry, right? So this is power here. So I suggest you spend time to really learn this chapter, right? And do the homeworks and learn this, because there's gonna come times in your research when the answer's not in the book. And there's no like good models that fit it, right? Of course, that's a bad thing to say. You should always try to find a good model, right? That's the whole point. Find a good model, but their model's probably very approximate. And one thing you could resort to is by doing this numerical solution, right? Now you can solve, you can do a lot of things with this, right? Okay, here's the far fields. We're going to compare the far fields from this strip to a couple of different numerical approaches. We're going to learn geometrical optics plus GTD, which is geometrical theory of diffraction. We're going to learn that next, after we're done with integral equations and method moments. All right, but before we get to that, we're going to have to learn a bunch of differential geometry. So I'm going to spend like a week or two teaching you guys mathematics, basically, differential geometry, which is the study of geometry in the framework of calculus, right? Curves, surfaces, curvature, the torsion, all of that. It's gonna be fun. Then you solve Maxwell's equations in the framework of differential geometry and under the assumption of what's called a asymptotic expansion, which is valid for high frequencies or electrically large, in other words. We'll get to that. It's a lot of fun. So GLGTD, that's one approach, yeah? Then there's physical optics here, which is this dashed line. Then there's physical optics plus PTD. So you can supplement physical optics with some currents that account for diffraction that's not modeled. That edge diffraction from the last slide, that physical optics didn't capture. You can model that using physical theory of diffraction. All right. And then the integral equation. Everything agrees perfectly except for PO, right? Everything's overlapping except for physical optics. Physical optics is very approximate, right? Works very well in the middle where the main beam is, first few side lobes, but it doesn't capture any of the edge effects. All of these other numerical algorithms capture edge effects: GTD, diffraction, PTD, diffraction. Integral equation is everything, right? That's I think the best thing you can do. Integral equation is numerically exact, right? All right. Good. Okay, any questions so far? You'll probably have some when you do your homework. So let's add impedance sheets. All right, so this boundary condition, I'm not going to derive it for you. I might later in this course. It comes from what's called a generalized sheet transition condition. That's one way to get to it, or it's known as an impedance boundary condition. But now we're going to redo everything we did for constructing the integral equations by knowing the total field on the left-hand side. We knew the total field on the left-hand side, which allowed us to only have the unknown as the current in the integrand, right? We knew that the total electric field had to equal 0 on PEC. So the left-hand side, we had a known value, we eliminated that, and we were left with the unknown only being the J underneath the integral. But now there's another boundary condition where we know what the total field has to be. And in fact, that boundary condition relates the total tangential field to the induced surface current through a proportionality constant called the sheet impedance. All right. This is kind of like one of the constitutive relations, which is J equal to Y into E, right? Or J equal to sigma E. You guys have seen that before, right? Current density is equal to sigma times the electric field, right? Well, if you divide both sides by sigma, then you get, no, you want to keep it that way, right? So J sigma E, all right? Well, you can also call this Y into E, where there's the electric admittance. It's okay, so I'm making this a very loose analogy, right? Because sigma is a volumetric material constant, bulk, right? It applies to the conductor geometry. But Y is a sheet impedance. It applies at a boundary. So don't take this direct. Don't go off doing some kind of research with this equality here. But know that the concepts are similar, right? So Y is a sheet parameter. And if you divide both sides of this expression by eta sheet, then you get then you get the same thing. All right? Anyhow, this is the new boundary condition called impedance boundary condition. E tangential is eta sheet times JS. What is eta sheet? We'll get to that, right? It's a sheet impedance. All right. Okay, so how do we construct this integral equation? We take the total electric field, which is the left-hand side of this boundary condition, and express it as incident plus scattered, and then we set that equal to A to C times J, right? As before. All right. Or as the boundary condition implies. Now, let's move the incident field to one side of the equation and everything else to the other. So what I'm going to do is move this term to the other side. And I get A to sheet times J minus E scattered, where E scattered now we express as the spatial convolution of the current density with the Green's function, right? Same as before, except what would be the difference between this and what we had before? It would be, we had E incident equal to negative E scattered. Here we have E incident equal to negative E scattered plus E total. And we know that if it's PC, E total is 0. So that means A to sheet has to be 0. So the sheet impedance for perfect electric conductor is 0. All right, then everything goes back to what it was before. All right. So for TE incidence, all right, TE means these are still two-dimensional problems. We're using the two-dimensional Green's function here, the Hankel function, for problems where the incidence is transverse electric. Now, the plane of incidence is the plane of the board, the 2D plane. Transverse electric means the electric field is in and out of the board. That's what we've been doing this whole lecture so far. Line source is in and out of the board and made the electric field incident in and out of the board. There's also transverse magnetic incidence where the magnetic field is in and out of the board and the electric field's in plane. For that case, the Green's function is slightly different. For that case, the Green's function is still Hankel, not 2, but it has these derivatives in front. 1 plus 1 over k naught squared partial by partial x squared. All right? It's a little more difficult, but not too much. Otherwise, the same. Look at this. Incident field is z-directed, current is z-directed for TE because the electric field is in and out of the board, which is the z-axis. But here for TM, the electric field is x-directed, right? And the current is x-directed. All right, good. All right, so should be very similar, right, to what you've, as long as you take for granted this boundary condition here, everything else is very easy, right? So this boundary condition, we'll get into it more. You can learn more about it in the metamaterials course that we teach here, or you can come to my office and I can give you some papers to read, right? Let me see if I had a paper here. I think it's in this paper. You might be able to find something similar in this paper. Or you can look at my paper, of course. I have a review paper in nanophotonics that kind of derives this boundary condition. Matter of fact, you can look there.
Are there any like simple equations for like calculating it based on whatever material parameters you want?
A to sheet. Yeah, you can relate A to sheet to epsilon. For example, that's what this paper does. This Velakis and Barkasheli. You'll read this for your homework, as a matter of fact. But here we want to do the design problem. We want to solve for what A to sheet we need to transform an incident field to a known scattered or desired scattered. So we know the incident field. Now we want to stipulate what the scattered field is that we want from this impedance sheet. And we want to solve the integral equation to find the current. Once we have the current and the stipulated total electric field, because we know the incident, we stipulate the desired scatter field that the metaserver is supposed to give us. Then we can back out the A sheet impedance by dividing both sides of this equation by J. All right? Okay. So it's more of the same, right? Here's our integral equation for TE, and we're going to discretize the geometry into pulse basis functions, which are 1 if x minus x prime is less than delta over 2. They have a width of delta. The centers of each of these pulses are the match points. Minus w over 2 puts us on the left end, and then we go half of a delta, puts us at the center of the first one, and then we move by an entire integer delta to go to the centers of each additional ones. All right? And we expand the current density in terms of pulse basis functions with unknown current complex coefficients. And the pulse basis function defined like this. Then we substitute the current density into the integral equation. But now take a look at this. The difference here is that our current density appears in 2 places, right? So we have to take this expansion and plug it into both places, right? So here we have, gosh, I can't put my palm on this thing without, oh my God, no way. Sorry. here we have the current once, and then here it is again with the pulse, right? So I left the pulse here, but not here. I don't know why. Okay. Anyway, yeah. So this is what it is, right? All right. Okay. All of the same, right? Point matching, aka co-location, you know what that is now. We test at XM. So we evaluate the incident field at XM. In other words, we integrated the left-hand side against a delta function of X minus XM, which means just evaluate the integrand at XM, right? Same thing with the right-hand side, but now, okay, so here we now evaluate this at XM, right? And we only integrate over the subdomain pulse expansion function. Here we pick up a delta Mn because these were defined for n, right? They were the n, the index n, 1, 2, 3, 4, 5 up to n. Then we integrate against a delta function at x minus xm. So this entire thing is only valid when x is equal to xm. Because if x is not equal to xm, then this entire thing goes to 0 because of the delta function. So you have to do the integrations, you'll see it. All right. So all this implies is that these sheet impedances are only going to appear on the diagonal of the matrix.
So now the coefficients will be the sheet impedance.
The coefficients. No,
The
at this-
basis function, they have some coefficients when we expand in basis. function.
Yes,
So what will be the coefficients?
they're still here, right?
Oh,
This current coefficients are in both terms. This is the total field, A to sheet times J. This is the scatter field term. They're in both terms, but they're weighted here by, the current is weighted by the sheet impedance. At this point, you assume you know the sheet impedances, right? Or else you can't solve this. But I'll show you how to solve it without knowing those at first. All right, so next, we define the matrices. V, the voltage vector, the left-hand side. Z sheet now is a new matrix. A to sheet times delta Mn, meaning that this delta Mn is 0. So delta Mn equals to 0 if M is not equal to N, 1 if M equals to N, right? So these appear, this is a diagonal matrix. All right, and then the ZMN matrix is the same. So, okay, so now here's our integral equation in matrix form. Vm equals to Z sheet In plus ZMN times In. Before we just had ZMN times In equal to Vm, right? Now we have this extra part, which is for the impedance sheet. We can factor out the IMs, we get Z sheet plus ZMN into IN, and we can solve for IN, assuming we knew the Z sheets. We knew these sheet impedances at all these match points, right? All right. And for the TM case, you get this impedance matrix. The derivative that we had to take of the H naught function, in this case, these derivatives of H naught, they led to H naught plus H2. Right? So the TM case has the Green's function splits into H naught plus H2. Because of this derivative, right? All right. So the self terms are the same, right? They're not any different than the previous case. The sheet impedance doesn't introduce self terms because we're not integrating Green's function in the sheet impedance. It's just Z sheet times I or J. So now this is the small argument expansion for the H2 and for the H naught. So the Z self terms for the TM case become this. And for the TE case, we've already seen, right? Okay, let's come back to this, yeah? All right, good. So your homework's due on Monday, yeah? You're gonna get another homework probably next Wednesday on all this moment method stuff, all right? And then we'll get into GTD and then Green's functions, and then we'll be done with the whole book. You've learned all of Bolanos's Advanced Engineering Electromagnetics, which is an advanced book. It's in the title. So you should be advanced electromagnetic engineers, yeah? Very good. All right, see you guys.
That's awesome.